Okay, in Lesson 9b, we're going to talk about some commonly occurring continuous probability models, and we'll also define expected value, or the mean value, for continuous probability model distributions. There are three commonly occurring continuous probability models: the normal model, the uniform model, and the exponential model. The normal model occurs so frequently and is used in so many ways that we're going to cover that in its own lesson in Lesson 10. But here we're going to consider the uniform and exponential models. So we'll talk about uniform probability model first. In some situations, all possible outcomes are equally likely, but the quantity we're considering is continuous. An example of this would be, let's say you're interested in the time that you wait for a bus when you arrive at a bus stop. That would definitely be a continuous amount of time, because you could wait anywhere from 0 seconds to 1 second to 3.8 seconds to 15 seconds to 25.8 seconds. There's a whole continuum of possible values there, as opposed to, say, a discrete possible outcomes, something like the number of roll on a six-sided dice, which can only have 1, 2, 3, 4, 5, or 6. So for a continuous variable where all outcomes are equally likely, like the wait time at a bus stop if you arrive at a random time, the probability density function must be a horizontal line, the same probability density in the area for every possible outcome. For example, let's look at that one that we just mentioned, the amount of time that you wait at a bus stop. If a bus arrives every 20 minutes, but you arrive at a random time at the bus stop, well, the time you would wait would be uniformly distributed. There's no particular reason where you would wait a longer or a shorter amount of time. So the shortest amount of time you could wait would be 0 minutes, and the longest amount of time you could wait would be 20 minutes, and all of the times in between would be equally likely to occur. So let's say we wanted to use a model that models that, and then find this question right here. What is the probability that on any given day you will wait between 5 and 10 minutes for the bus? Okay, so the problem states that the probability is distributed uniformly, or at least it's implied, and the possible values are between 0 and 20 minutes. So we could start by sketching a uniform probability density function, which would be a line. So f of x equals some sort of a constant here, and this is defined only for time values between 0 and 20 minutes. The function will be a constant. F of x is a constant, but what would that constant be? All right, well, we know that the total area under the curve represents the probability, and the area of all the possibilities, the sum of the probabilities from 0 to 20, has to sum to 100%, and therefore the area under this curve has to equal 1 for this f of x to be a probability density function. So the width of this rectangle that we've shaded here in blue is 20. But that means that the height would have to be 1/20th, so that if I took width times height, the 20 times 1/20th, that would multiply to give me an area of 1, because the rectangle, the area of a rectangle is length times width. So this height has to be 1/20th, and therefore the probability density function would have to be f of x is the constant 1 over 20. Now, not 1 over 20 times x, because that means it would change depending on the x value. This is just the constant 1/20th. Okay, now that we have the probability density function defined as 1/20th, we could find the probability that you would wait between 5 and 10 minutes. Now, we'll have to use calculus for this. We'll have to use an integral, because we don't have a uniform model CDF function on our calculators, but if we know basic calculus, this is easy to do. The probability that the wait time x is between 5 and 10 would simply be the area under the curve from 5 to 10, and therefore the integral from 5 to 10 of 1 over 20 dx. And you can use various techniques to compute that and get that that's 0.25. So that means there's a 1/4 chance that we'll wait between 5 and 10 minutes if the bus arrives every 20 minutes. Okay, so that is the uniform model, and uniform just means that the density is constant for all possible values in the range that is allowed. The second common continuous probability model that we sometimes encounter is called the exponential model. And this covers situations where outcomes close to 0 are very likely, but the probability of an outcome becomes less and less likely the higher the value that we have. So these situations, we use what's called an exponential continuous probability model. It's actually kind of the continuous probability analog to the geometric model. The geometric model also had this behavior that the lowest case, that the flip would occur, say if we're counting the number of times we have to flip a coin until we get a head, it's most likely to occur on the first flip and then gets progressively less likely because we have to have the failure probability multiplied multiple times, a geometric progression. Right, so this exponential model is sort of the continuous version of that. It has the same general shape as the geometric discrete model. The actual model is given, the formula for it is given by this function right here. F of x is lambda times e to the negative lambda x. And the reason this is a negative lambda is because it's a negative exponential, because it's exponential decay. And this lambda in this context is referred to as the rate parameter. And we would have to be given that, or given some information we could use to solve for that if we were solving a problem with probability that had an exponential model. It would be something where the likelihood is close to the low end of the curve and gets less and less likely as we go further out. Okay, so just like with uniform probability density model, there's no CDF calculator function for an exponential model, so we would have to use calculus and an integral to find probabilities with an exponential model. So we have these two models, the uniform model, the exponential model. And we also have the normal probability model, but we typically don't use calculus for that because there are calculator functions to do that without calculus. There are a number of other probability models besides uniform, exponential, and normal. I'm going to mention a few others here, but we're not going to cover them in any detail. This is mainly for AP statistics students that will encounter some of these. There's one called the student t-distribution. That's symmetrical like a normal curve, but it's a little wider. There's more variability and more probability in the tails. That's used in statistics courses for inference calculations that involve means or regression line analysis. So if you're in AP statistics, just know that the student t-distribution is another example of a continuous probability model. Also for AP statistics students, there's a distribution called a chi-squared distribution. That's not symmetrical, typically skewed right. In fact, it's always skewed right. It looks something like this. And it's used in statistics for comparing problems where we have counts or proportions, but we have more than two populations that we're comparing. And then not so much in AP statistics, but in introductory statistics courses in college, there's another type of distribution called an F distribution that's also not symmetrical, and that's used when we're comparing more than two populations of means in an analysis technique called ANOVA, which stands for analysis of variance. So all of these are different continuous probability models, and areas under the curve are used to find the probability of any particular test statistic occurring, just like we did for the uniform model and for the exponential model. Okay, but one thing I do want to talk about as we wrap this up is how do we find the mean or the expected value for continuous probability models? For discrete probability models, we said that the probabilities form a distribution across the outcomes, and this distribution has a mean and a standard deviation. The mean is also referred to as the expected value or sometimes the average value. The difference is that the average value assumes that the outcomes are all equally likely, and the expected value is weighted by the probabilities. So let's take an example. We'll go back to the discrete model just to kind of introduce this idea, and then we'll talk about the continuous version of this. So for discrete probability models, the expected value is given by the expected value formula. And a raffle is, I think, the best way to kind of understand the concept of it. Let's say that you're talking about a raffle. There's 100 tickets. One of them is a winner that wins $50. Two of them are second place tickets that win $5 each, and the other 97 tickets are losing tickets and they win $0. So the expected value would be each winning's value, $50 in this case, times its probability of 1/100th, plus the value $5 times its probability that happens 2 out of 100 times, plus $0 or 197 out of 100 times. So if you take every data value and multiply its probability and then sum all those up, you get what's called the expected value, which in this case is 60 cents. Now 60 cents is not an actual achievable winning. You can only win $0, $5, or $50, but the expected value means that if you were to play this raffle, many times, then on average you would win 60 cents per play. Right? And so therefore you shouldn't, if you're paying more than 60 cents to play this raffle, then you're going to lose money in the long run. Okay. So we could think of it this way. Expected value is the sum of a data value times its probability. Okay, so for continuous probability models, what we're going to do is just take those same ideas but translate them into continuous variable space. So the data value here is x, and the probability value, that just becomes the probability density function here. So this is the data value times the probability density function. And then we're taking the sum, so the integral, the sum from the lowest x to the highest x. So the summation becomes an integral. So the formula to find the expected value is just the integral from over the entire range of possible values of the probability density function times x. And the way I remember it is that we have to multiply the probability density function by an extra x. So the expected value requires an extra x. But it's just the continuous analog of the discrete probability value or expected value formula. So let's take an example here. Let's say lengths of steel bars are produced by some steel cutting machine, and they vary from bar to bar between a minimum length of 23 centimeters and a maximum length of 38 centimeters. The variation is not uniform, but it's described instead by this given probability density function. So they give this f of x. That means I can plug a length value in for x, and this tells me the probability density in that region of the probability density distribution there. So what is the expected value, the mean, of the distribution of steel bar lengths? In other words, what would be the most expected steel bar length, the expected value? Okay, so what we can do is just take the expected value formula, which says to take the integral from the min to the max value of the probability density function times an x. And I'm realizing I'm missing a little dx there, so think about there's a dx there. Okay, so here's the value of that. It turns out to be I'm missing the integral. That would be integral from 23 to 38 of the probability density function times dx times an extra x. And that turns out to be 33.39 centimeters. So that means that as long as we have the probability density for each length value, we can use an integral to find the typical value. So a typical bar that comes off of this machine would be 33.39 centimeters in length. Okay, so when finding expected value, don't forget the extra x, because the x represents the data value. Oh, and don't forget your dx either. Okay. So calculus courses, by the way, for those that are calculus students, they also mention a second way to find something that we call the typical value for a distribution, the average value. So how does that compare to the expected value? The formula that's typically given for average value is this. It's the integral from a to b of the probability density function times 1 over b minus a. But I think of it this way, as the integral divided by b minus a. So where does that come from? Average value is based on the same procedure we use to find the arithmetic average if we have discrete units. Let's say that we have 5 numbers, 7, 18, 27, 31, and 120, and we want to find the average value. Then we just add them up, take the sum of all the elements, and we divide by the number of elements, which is 5. That gives us the average value. So the continuous version of this is we use an integral to sum up all the values, and then the number of elements is represented by the width of the x values. The width of the variable value is b minus a. So it's really just the continuous version of taking an average. Right, so what's the difference between expected value and average value? Because these formulas are both provided in a typical entry-level calculus course. So average value, in that case, the f of x is actually the thing we're trying to find the value of. So f of x is not a probability density function. We don't have a probability density function. It's just f of x is the value itself. And because there is no probability density function, average value makes the assumption that all of these f of x values are equally likely. So average value is an average of the f of x values, where f of x is the value. Okay, expected value, The value that we're finding is the x. This is the value. And the f of x gives the probability density of the x values, right? So expected value, you can think of it as an average that's been weighted by the probability density function. So which one should you use? It really comes down to what is the f of x. If the f of x is a probability density function, then you have to use the expected value. If the f of x is the value itself, then you have to use the average value. That's how we tell which one we use for typical value. Okay, so just a summary here of what we covered in the last couple of videos. We said that we can define a continuous distribution as opposed to discrete. Where discrete variables are taking on only specific values, continuous variables can take on any value, sometimes within a specified limit. And then discrete situations often involve counting, and we're often counting the number of items in specific categories, so discrete variables are sometimes referred to as categorical or sometimes qualitative variables. Continuous variables always involve a variable that's numerical and often includes units, so continuous variables are sometimes referred to as numerical or quantitative. So qualitative is discrete and quantitative is continuous. For discrete situations, we can use sometimes models like the binomial or the geometric model to analyze probability, and all those other counting related things, equally likely cases and or rules, all those sorts of things also apply for discrete situations, right? And we have an expected value formula that we can use to find the mean of a general discrete distribution with a probability model. For continuous, we've now learned that we need to use an integral to find the area under the curve between boundaries to find probability, and we have expected value and average value formulas depending on what the f of x represents. Okay, there are three kind of general continuous probability models that we see. There's the uniform model, where we have a horizontal line and f of x is a constant. We have the exponential model, where f of x is this negative exponential decay, where lambda is the rate parameter. And for both of those situations, we would use an integral to find the probability that the variable x is between any values c and d, where f of x is a probability density function. Although we're not going to talk about this until the next lesson, lesson 10, there is a function here for generating the normal or Gaussian or bell curve. It's this complicated negative exponential function, has a mean and a standard deviation, and we're going to learn that we can use calculus, or more frequently we use the built-in normal CDF and inverse normal calculator functions. We'll cover that as well, but I'm listing these because these three are the most commonly found continuous probability models. And regardless of which model we're talking about, the expected value for discrete data is the sum of data values times their probabilities. So the continuous version of that is the integral of the probability density function times the x, which is the variable. And the average value is the sum of all the values divided by the number of elements for discrete. For continuous, it's the integral for the sum of all the elements divided by the width of the variables that represents the number of elements. And the difference is that the expected value, the f of x represents a probability density function and x is the variable, and for the average value, that's when f of x represents the value itself. Okay, that wraps up continuous probability models except for a discussion of the normal probability model, so we'll talk about that in lesson 10.